In this video, we'll talk about how to compute definite integrals as signed areas when the shape of our graph is nice and we can figure out the area just using geometry. So recall that in the last video, we defined what a definite integral was. So our notation for it is we wrote an integral from a to b. So the a and the b, these numbers are sometimes either called the limits of integration. The limits of integration, or the bounds. So I'll be using that terminology to refer to those. So a to b, f of x dx. That's our notation for a definite integral. And this was equal to the limit as n goes to infinity of our Riemann sum. The sum from I equals 1 to n delta x times f of x sub I. And we said that this represented a signed area. So let's explain what that means with a picture, with an example. So let's suppose that we have the following example. So I have this function, which consists of a straight line segment from -3, -4, all the way to 2, 6, and then the semicircle portion, and then a straight sort of ray off to the side, horizontally. And I want to evaluate the definite integral from -3 to 6, f of x dx, which means I want to figure out from the point where x is -3 to the point where x is 6, what's the area under the graph? But with definite integrals, we think of them as signed areas. So let's talk about what that means. So when there's a portion like this first sort of triangular section over here that is underneath the graph, I'm going to call this area A1, that's going to get counted as a negative area. So when I start to write down what this definite integral is equal to, I'm going to count that first area as being negative. So the negative A1. Okay, and then how do I figure out the area of the rest of this graph? Well, I see that if I were to draw a dashed line up here, that I get another triangle. I'm going to call this A2. Write that a little bit better. A2. And that's going to be a positive area because that part is above the curve. So A2. And then there's one more region over here, A3. So that is also positive. Okay, so regions below x-axis count as negative areas. Okay, so for area 1, that one's easy because it's a triangle. I have that negative in front. It gets considered as a negative area because that part of the curve is below the x-axis, and regions below the x-axis count as negative areas. Okay, so I get -1/2 base times height. And the base of that triangle is 2, and the height is 4. For area 2, that's also a triangle, but it counts as a positive area because the graph there is above the x-axis. So I'll get +1/2 base times height. And the base of that triangle is 3, and the height is 6. So for area 3, so for the area of this third region, let's write that better. Okay, so for A3, I want to give you the chance to think about what this area would be, because this is the most challenging out of the 3. So pause the video for about 2 minutes, 1 to 2 minutes, and try to figure out what area 3 would be. So 4, 3, 2, 1, pause the video. Pause the video and think about what A3 would be for about 2 minutes. All right, so hopefully you've done that. Hopefully you paused that video for about 2 minutes to really try and think about how would we get A3. So for A3, if I were to draw this region one more time that A3 is, I have this sort of shape, sort of like 3 sides of a rectangle, and then a semicircle extending down like this. So one way I could get that is, if I first think about sort of completing this rectangle, and I could see the dimensions of that rectangle. Like from this point to this point, that's a distance of 4. And the height of that rectangle is 6. So if I were to take the area of that rectangle and subtract away this semicircle, we would end up with what we want. So area 3 is the area of the rectangle minus the area of that semicircle. All right, let's compute these now. Okay, so for this first term, the 2's cancel, and I'll get -4. For the next term, 3 times 6 is 18, divided by 2 is 9. Okay, and then plus the area of the rectangle, 4 times 6, that's 24. The area of a semicircle would be, so I have that minus in front of it, we're subtracting the area of the semicircle. Area of the semicircle is 1/2 pi r squared. And the radius of that semicircle, I can see from the picture, it's drawn to be 2 here. So 2 squared. Okay, so simplifying this, we will end up with 29. That's what the first three terms combine to. And then minus 2 squared is 4. 4 divided by 2 is 2. So minus 2 pi. All right, so let's look at another example. Okay, so in this example, I want to evaluate the definite integral. But this time, I don't have a graph of a function. I have a formula. So I want the definite integral from 0 to 3 of the square root of 9 minus x squared dx. So we know that definite integrals represent signed areas under a graph. So it would be helpful to know what this graph looks like. So let's try to graph it. So this is where some algebra review comes in. Take about 30 seconds to see if you remember, what does the graph of this function look like? 4, 3, 2, 1, pause the video. Pause it for 30 seconds and see if you can remember what this graph looks like without using a graphing calculator. All right, so hopefully you did that. Hopefully you paused it for about 30 seconds to try to graph this. So, but no worries if you don't remember what the graph looks like. We're going to review it. So recall that when you have x squared plus y squared equals r squared, this is a circle with center 0, 0 and radius r. So looking at this, it might not be clear. Wait, this looks different from what I have. I have the square root of some number minus x squared. But it turns out it's derived from a circle equation, and we'll talk about how. So if I had x squared plus y squared equals 9, which isn't exactly what I have, but if I did have this, that would be a circle. Its centered is at the origin, 0, 0. And r squared is 9. So that means the radius would be the square root of that, which is 3. So it would go 3 in each direction. And it would look something like this. So this is -3, and that's -3. Okay, so what I'm going to do now with this circle equation is isolate the y. So we get y squared equals 9 minus x squared. And then to get rid of that squared, I square root this. Square root both sides. And that gives us y equals square root, let's write that better, square root of 9 minus x squared, but anytime I take an even root of both sides of an equation, I gotta put a plus or minus. That's also some review from algebra. So we get two possibilities. Either y equals the positive square root of 9 minus x squared, or y equals the negative square root of 9 minus x squared. So what do each of these on their own look like? So if I draw some axes, when we have y equals this positive square root, one of the things that happens is no matter what you plug into the square root, after you do the actual square root, the output is always going to be non-negative. So in this equation, the y is non-negative, which means it can't be the whole circle. It's only going to be the part of the circle where the y values are non-negative. and that is the top half. So this would be -3, that's 3, and that's 3, and that's what the graph of y equals square root of 9 minus x squared looks like. If we had a negative in front of the square root, that would be, I'm not going to draw this one, but this would be the bottom half of the circle. Because when you have that negative in front of the square root, now it means that all of the y values are not positive. And if all the y values are not positive, that means we're looking at the bottom half of that semicircle. Okay, so now we know the shape of our graph. We know it's a semicircle. But we care about the area from x is 0 to 3, because those are the bounds of our integral. So we care about what's going on from when x is 0 to where x is 3, and that's this part of the graph. So we actually want the area of a quarter circle. So the integral from 0 to 3 of our function, based off of the bounds, this is a quarter circle, so the area would be 1/4 pi r squared. So pi r squared, and the radius of the circle is 3. So this gives us 9 pi over 4. And that's our integral right there. So the key to doing this question is really recognizing what does the graph of it look like, so that I can figure out this definite integral based off of the area under the graph. So one of the things that we might be able to tell from this is, this would only work if my graph is nice, like if it's things like straight lines that give me triangles or squares or rectangles, or perfect circular portions. So I want to end this video by listing the methods to compute definite integrals. We have 3 ways that we're going to talk about in our class. The first is with a Riemann sum. That was the limit of a Riemann sum. And we did that in the last video, an example of it. But this is very tedious. It's very tedious, and it only works for low degree polynomials. So as we saw in the last video when we did an example actually computing a limit of a Riemann sum, we needed some of those formulas, those sigma notation formulas for like I equals 1 to n of maybe I squared and what this equals. Well, we don't have a formula, like a nice formula for every single type of function. Like, you know, we only have formulas like this for the sum from I equals 1 to n of like 1 and I squared. There are others beyond that, but we're not going to talk about those in our class. They're a bit beyond the scope of our class. So there's a very limited number of functions that this would work for. The second way we can figure out a definite integral is what we talked about in this video, which is using areas. So either if we know the graph and the shapes are nice, or if we can draw the graph and the shapes are nice, we could do it just computing the areas. But this only works if the shapes are simple. So e.g., which means for example, e.g., if we're talking about linear pieces or circular pieces, I'm going to say path. If there's a linear or circular path. Okay, so there's one other way that we will talk about to compute definite integrals, which is called the fundamental theorem, which I'm going to abbreviate as THM, theorem of calculus. And this is maybe the most important result in all of calculus. And that's why it's called the fundamental theorem of calculus. And this is the topic of section 6.4. So we will look at that starting in the next video. But the thing that makes this so important is the fundamental theorem of calculus will connect. This connects the problem of finding an area under a graph with antiderivatives. It turns out there's a connection between getting an antiderivative of a function and finding the area of a function, finding the area under the graph of a function. And sort of initially, there's no reason to think why that would be the case. So that's pretty interesting, and it turns out very useful. So in terms of our goals for this section, we have finished our fifth goal, which is computing a definite integral using areas when the shape of our graph is simple enough to become shapes like rectangles and triangles and circles.